In the vast expanse of the universe, there exists a phenomenon so powerful, so mysterious, that it defies everything we think we know about reality: black holes. These cosmic enigmas, with their immense gravitational pull, can bend light, warp time, and even swallow entire stars without a trace. But what if black holes are more than just cosmic vacuum cleaners? What if they hold the answers to questions we haven't even dared to ask? Today, we're diving into 25 mind-bending theories about black holes that could reshape our understanding of the universe. From portals to other dimensions to the ultimate fate of space and time, these ideas push the boundaries of science and imagination. So, if you're ready to embark on a journey into the unknown, where the laws of physics as we know them might not apply, stay with us. By the end of this video, you'll see black holes in a whole new light, and maybe, just maybe, you'll glimpse the mysteries they've been hiding all along. Now, let's step into the first theory, one that feels like it's straight out of science fiction but has a surprising amount of scientific grounding. Black holes might not just be cosmic traps, they could actually be gateways to other universes. Imagine falling into a black hole, and instead of being crushed into oblivion, you emerge in a completely different reality. This idea hinges on the concept of wormholes, hypothetical tunnels through space-time that could connect distant parts of the universe or even entirely separate universes. Theoretical physics suggests that the extreme conditions inside a black hole could create these wormholes, bending the fabric of space-time in ways that defy our current understanding. If this is true, black holes wouldn't just be endpoints, they'd be bridges to places beyond our wildest imagination. Of course, the implications are staggering. Not only could this open the door to interstellar travel, but it could also challenge our understanding of time itself. Could black holes be the key to unlocking the secrets of parallel universes? For now, it remains a tantalizing possibility, one that keeps scientists and dreamers alike captivated by the mysteries of the cosmos. Shifting our gaze to another mind-bending concept, let's explore the holographic principle. This theory flips our understanding of black holes on its head by suggesting that all the information about what falls into a black hole isn't lost but is instead encoded on its surface, much like a hologram. Imagine a holographic sticker. It appears three-dimensional, but all its information is stored on a flat, two-dimensional surface. Similarly, the holographic principle proposes that the vast complexity of a black hole's interior can be fully described by data on its event horizon, the boundary beyond which nothing can escape. This idea challenges the conventional view of reality, suggesting that our three-dimensional universe might actually be a projection of information stored on a two-dimensional surface. It's a radical shift in thinking, one that could reconcile the laws of quantum mechanics with the principles of general relativity. If true, it would mean that black holes aren't just cosmic enigmas, but also the key to understanding the very fabric of reality itself. The implications are profound, raising questions about the nature of space, time, and the conservation of information. Could everything we perceive be a kind of cosmic hologram? The holographic principle invites us to reconsider the very foundations of our understanding of the universe. Now, let's turn our attention to a theory that strips black holes down to their most basic characteristics, the no-hair theorem. This intriguing idea suggests that black holes, despite their immense complexity, can be fully described using just three properties: mass, charge, and spin. In essence, it's as though black holes have no hair, meaning no additional details or features beyond these three fundamental traits. This simplicity might seem surprising, especially when you consider how mysterious and chaotic black holes appear. But the no-hair theorem argues that no matter what falls into a black hole, whether it's stars, planets, or even entire galaxies, all the information about those objects gets erased, leaving behind only these three defining attributes. However, like many theories in physics, the no-hair theorem isn't without its controversies. some scientists argue that black holes might indeed have hair or additional properties that the theorem doesn't account for. For example, quantum effects could introduce subtle complexities that challenge the simplicity of this model. There's also the question of whether magnetic fields or other phenomena might leave detectable traces on black holes, potentially adding more layers to their description. These exceptions and debates keep the no-hair theorem a living, evolving idea in the study of black holes. The theorem's implications are profound. If black holes truly are as simple as mass, charge, and spin, it could help us better understand their behavior and their role in the universe. But if they're more complex, it might mean we need to rethink our understanding of gravity and space-time altogether. Either way, the no-hair theorem invites us to ponder just how much we can learn about these cosmic giants and how much still remains hidden in their shadows. This ongoing exploration keeps the mystery of black holes alive and fuels our curiosity about the fundamental nature of the cosmos. Now, let's venture into a theory that turns the very fabric of our understanding of black holes on its head: the firewall paradox. Picture this: as you approach a black hole's event horizon, the point of no return, you expect to experience nothing out of the ordinary. According to Einstein's general relativity, you should glide smoothly across it, unaware of the immense gravitational forces at play. But here's where things get mind-bending. The firewall paradox suggests that instead of a smooth passage, an intense wall of energy could be waiting at the event horizon, incinerating anything that comes too close. This idea completely contradicts our traditional understanding of black holes. So, where does this paradox come from? It arises from the clash between two pillars of modern physics: general relativity and quantum mechanics. General relativity tells us that space-time is continuous, and the event horizon is just another part of space. Quantum mechanics, however, introduces the idea that information can't be destroyed. When matter falls into a black hole, what happens to all the information it contains? According to some interpretations, this information might be encoded in radiation near the event horizon, creating a firewall of energy in the process. This paradox has sparked heated debates among physicists. If firewalls exist, they would mean that the event horizon isn't the smooth, uneventful boundary we once thought it was. Instead, it could be a site of extreme energy and chaos, fundamentally altering our understanding of black holes. On the other hand, if firewalls don't exist, we're left with the challenge of explaining how information is preserved without violating quantum mechanics. Either way, the firewall paradox forces us to rethink the nature of space, time, and the very laws that govern the universe. The implications of this theory are profound. It not only challenges our understanding of black holes, but also pushes us to explore the boundaries between general relativity and quantum mechanics. Could there be a deeper theory that reconciles these two frameworks? Or does the firewall paradox hint at something entirely new about the nature of reality? As we continue to probe these questions, the firewall paradox stands as a testament to how black holes keep pushing the limits of our knowledge, reminding us that even the strangest theories could hold a kernel of truth. Shifting our gaze to another fascinating possibility, let's explore the theory that black holes might be the cosmic factories of dark matter. This idea suggests that these mysterious objects could play a key role in generating the invisible substance that makes up a significant portion of the universe. Dark matter, which doesn't emit, absorb, or reflect light, has puzzled scientists for decades, yet black holes might hold the key to understanding its origins. The theory proposes that black holes could produce dark matter through processes occurring near their event horizons or even within their interiors. One mechanism involves the creation of exotic particles during the intense gravitational interactions around black holes. These particles, unlike anything we've observed so far, could be the building blocks of dark matter. Another possibility is that black holes convert ordinary matter into dark matter through interactions we haven't yet discovered. Evidence supporting this idea comes from observations of black holes and their surrounding environments. For instance, the behavior of matter and radiation near black holes doesn't always align with predictions based solely on known physics. These anomalies could hint at the presence of dark matter being generated or influenced by black holes. Additionally, the distribution of dark matter in galaxies often correlates with the locations of supermassive black holes, suggesting a potential connection between the two. This theory isn't just a wild speculation, it's grounded in efforts to bridge gaps in our understanding of the universe. If black holes are indeed producing dark matter, it could explain why we've struggled to detect it directly. Instead of searching for dark matter in isolation, we might need to focus on the interactions and outputs of black holes. This approach could open new avenues for discovery, shedding light on one of the greatest mysteries in modern science. The implications are profound. If black holes are dark matter factories, they would play an even more central role in shaping the cosmos. This idea challenges us to rethink how black holes interact with their surroundings and how they contribute to the universe's structure. As we continue to explore this theory, we're reminded once again that black holes aren't just cosmic vacuums. They could be engines of creation, shaping the very fabric of the universe in ways we're only beginning to understand. Now, let's unravel one of the most perplexing mysteries surrounding black holes, the information paradox. This theory challenges our understanding of what happens to information that falls into these cosmic enigmas. According to the laws of quantum mechanics, information cannot be destroyed. Yet, when matter is pulled into a black hole, it seems to vanish, leaving us with a fundamental question: where does the information go? At the heart of this paradox lies the behavior of black holes as predicted by general relativity. Once something crosses the event horizon, it's lost to the outside universe, seemingly erased from existence. This conflicts with quantum principles, which insist that information must be conserved. The paradox forces us to confront a deep incompatibility between two of the most successful theories in physics. One potential solution comes from Stephen Hawking's groundbreaking work on Hawking radiation. This theory suggests that black holes aren't completely black. They emit tiny amounts of radiation over time, slowly losing mass. Hawking proposed that this radiation could carry away information about the matter that fell into the black hole, preserving it in some form. However, this idea isn't without its challenges. The radiation appears random, making it unclear how it could encode specific information about what entered the black hole. Another intriguing possibility involves quantum entanglement. This phenomenon, where particles become interconnected regardless of distance, might play a role in preserving information. Some theories suggest that information could be transferred to particles outside the black hole through entanglement, effectively escaping the event horizon. While this idea is still speculative, it offers a potential pathway to resolving the paradox by keeping information intact in the universe. The information paradox isn't just a theoretical puzzle, it has profound implications for our understanding of reality. If information is truly lost in black holes, it would require rewriting the laws of physics as we know them. On the other hand, if information is preserved, it could reveal deeper truths about the interplay between quantum mechanics and gravity. This paradox is a testament to the enduring mystery of black holes, reminding us that even the most well-studied objects in the universe still hold secrets waiting to be uncovered. Now, shifting our gaze to the very beginnings of the cosmos, let's explore the fascinating concept of primordial black holes. Unlike the black holes we're familiar with, which form from collapsing stars, these ancient entities are thought to have emerged in the early universe mere moments after the Big Bang. The intense density and temperature fluctuations of that primordial soup could have created pockets of matter so dense that they collapsed directly into black holes, bypassing the need for stars altogether. These primordial black holes are intriguing not just because of their origins, but also because they might hold the key to some of the universe's greatest mysteries. One of the most compelling theories suggests that they could be responsible for dark matter, the invisible substance that makes up a significant portion of the universe's mass. While dark matter has never been directly observed, its gravitational effects are undeniable. If primordial black holes exist in vast numbers, their combined mass could account for the missing dark matter, offering a potential solution to this long-standing puzzle. Another fascinating aspect of these early black holes is their potential role in shaping the cosmos. If they were abundant in the early universe, their gravitational pull could have influenced the formation of galaxies and large-scale structures. Some theories even propose that they acted as seeds for supermassive black holes, which now reside at the centers of galaxies. This would mean that primordial black holes weren't just relics of the early universe, they were active participants in its evolution. Despite their theoretical appeal, primordial black holes remain elusive. Detecting them is a significant challenge, as they could range in size from subatomic to solar masses. Smaller ones might have evaporated by now due to Hawking radiation, while larger ones could be hiding in plain sight, masquerading as ordinary black holes. Astronomers are actively searching for evidence, using techniques like gravitational lensing and observations of cosmic microwave background radiation to uncover their traces. The idea of primordial black holes invites us to reconsider the early universe as a place of incredible complexity and possibility. If they exist, they could rewrite our understanding of cosmic history, dark matter, and the very fabric of space and time. As we continue to probe the mysteries of the universe, these ancient enigmas remind us that the story of black holes and the cosmos itself is far from complete. Now, let's take a leap into the realm of science fiction turned potential reality, the idea of black hole starships. Imagine harnessing the immense power of a black hole to propel a spacecraft across the vast distances of the universe. This concept, while speculative, is grounded in some fascinating scientific principles. At the heart of this idea is the notion that black holes could serve as incredibly efficient energy sources. One proposed method involves using the energy released by matter as it spirals into a black hole's event horizon, a process known as accretion. As matter falls in, it heats up and emits radiation, which could theoretically be captured and converted into thrust. Think of it as a cosmic engine drawing power from one of the universe's most extreme environments. Another intriguing approach is the Penrose process, which suggests that energy could be extracted from the rotation of a black hole. By exploiting the ergosphere, a region outside the event horizon where spacetime is dragged along with the black holes, a spacecraft could steal some of this rotational energy. This method could potentially provide a vast amount of power, far beyond what conventional propulsion systems could offer. Of course, the challenges are immense. Creating and controlling a miniature black hole, for instance, would require technology far beyond our current capabilities. The risks of such a venture are equally daunting. Anything from a miscalculation to a malfunction could result in catastrophic consequences. Additionally, the ethical and safety implications of wielding such a powerful force are profound. Despite these hurdles, the concept of black hole starships opens up exciting possibilities for interstellar travel. If humanity ever hopes to reach the stars, we'll need to think beyond the limits of traditional fuel sources. Black holes, with their boundless energy, offer a tantalizing glimpse into what the future of space exploration might hold. While it remains a speculative idea, it's a testament to the power of human imagination and our relentless drive to explore the unknown. As we venture further into the cosmos, the boundaries of what's possible continue to expand. Next, we'll shift our focus to another mind-bending theory, the idea that black holes could function as quantum computers, processing information at speeds that defy comprehension. Shifting our gaze to the cutting edge of theoretical physics, let's explore the mind-bending idea that black holes could act as quantum computers. This theory suggests that the immense gravitational pull and extreme conditions within a black hole might enable it to process information at speeds far beyond anything we've ever conceived. To understand how this could work, we need to dive into the strange world of quantum mechanics. At the quantum level, particles can exist in multiple states simultaneously, a phenomenon known as superposition. This property is the foundation of quantum computing, which leverages these states to perform calculations at unprecedented speeds. Black holes, with their intense gravitational fields, could amplify these quantum effects. Some scientists propose that the event horizon of a black hole might act as a kind of quantum processor, where information is encoded and manipulated in ways we can't yet fully comprehend. One key aspect of this theory revolves around the concept of quantum entanglement, where particles become linked in such a way that the state of one instantly influences the state of another, regardless of distance. Black holes, with their ability to warp space and time, could create and sustain entangled states on a massive scale. This could allow for the processing of vast amounts of information in parallel, far exceeding the capabilities of any computer we've built. The implications of black hole quantum computing are staggering. If harnessed, it could revolutionize fields like cryptography, material science, and artificial intelligence. Imagine solving complex problems in seconds that would take current supercomputers centuries. The sheer scale of a black hole's processing power could unlock secrets of the universe itself, from the nature of dark matter to the origins of cosmic structures. However, the challenges are equally immense. Manipulating a black hole for computing purposes would require technology and understanding far beyond our current reach. The risks are equally daunting. Miscalculations could lead to catastrophic outcomes. Yet, the very idea pushes the boundaries of what we consider possible, forcing us to rethink the relationship between gravity, quantum mechanics, and information processing. As we continue to unravel the mysteries of black holes, the concept of quantum computing within these cosmic giants offers a tantalizing glimpse into the future of physics and technology. It's a reminder that the universe, in all its complexity, still holds countless surprises waiting to be discovered. Next, we'll turn our attention to the cosmic censorship hypothesis, a theory that explores the hidden nature of black hole singularities. Moving forward in our exploration of black hole mysteries, we encounter the cosmic censorship hypothesis. This intriguing theory suggests that singularities, those infinitely dense and small points at the center of black holes, are always hidden behind event horizons. In other words, the universe has a kind of cosmic rule, preventing naked singularities from existing in plain view. The idea, first proposed by physicist Roger Penrose, aims to preserve the predictability of the universe by ensuring that singularities remain shrouded and inaccessible. The reasoning behind this hypothesis is rooted in the laws of physics. According to general relativity, singularities are points where the laws of physics as we know them break down. If a singularity were exposed without an event horizon, its extreme gravitational effects could lead to unpredictable and potentially chaotic outcomes. The cosmic censorship hypothesis acts as a safeguard, ensuring that these anomalies remain contained within the boundaries of a black hole where their influence is limited. However, this theory isn't without its challenges. Some mathematical models and theoretical scenarios suggest that naked singularities might indeed be possible under certain conditions. For instance, if a black hole were to spin at an extremely high rate, or if two black holes collided in just the right way, it's possible that a singularity could become exposed. These exceptions raise questions about the robustness of the hypothesis and whether the universe truly enforces such a rule. The debate over cosmic censorship continues to spark discussions among physicists. If naked singularities do exist, they could offer a unique window into the fundamental nature of space and time, potentially revealing new insights into the interplay between general relativity and quantum mechanics. On the other hand, if the hypothesis holds true, it reinforces the idea that the universe operates with a kind of cosmic order, even in the face of extreme phenomena. While the cosmic censorship hypothesis remains unproven, it serves as a fascinating framework for understanding the behavior of black holes and the universe's broader rules. As we continue to study these cosmic enigmas, we may uncover whether singularities are always hidden, or if the universe occasionally lets its secrets slip out. Up next, we'll delve into the effects of black holes on time itself, exploring the fascinating phenomenon of time dilation. Now, let's shift our focus to one of the most mind-bending effects of black holes, time dilation. Imagine standing near a black hole where the gravitational pull is so immense that it warps the very fabric of space and time. For you, time would pass normally, but to an observer far away, it would appear as though your clock has slowed down drastically. This is the essence of time dilation, a phenomenon predicted by Einstein's theory of general relativity. The closer you get to a black hole's event horizon, the more extreme this effect becomes. At the horizon itself, time would seem to come to a complete standstill from an outsider's perspective. Yet for you, time would continue to flow as usual. This strange behavior isn't just a quirk of black holes. It's a fundamental aspect of how gravity interacts with time. The stronger the gravitational field, the more time slows down. This phenomenon isn't just theoretical. It's been observed on a smaller scale. For example, atomic clocks on Earth run slightly slower at sea level compared to those on mountaintops where gravity is weaker. Near a black hole, however, the effect is magnified to an extraordinary degree. If you were to orbit a black hole for a few hours, decades or even centuries could pass for those far away. Time dilation around black holes also has profound implications for our understanding of space-time. It challenges our intuitive notions of time as a constant, universal flow, and instead reveals it as a flexible, dynamic dimension shaped by gravity. This concept is crucial for understanding the behavior of objects in extreme environments, such as the centers of galaxies where supermassive black holes reside. Moreover, time dilation could play a role in resolving some of the paradoxes associated with black holes, such as the fate of information that falls into them. If time slows down near the event horizon, perhaps the information isn't lost forever, but instead stretched across the fabric of space-time in ways we're only beginning to comprehend. As we continue to explore the mysteries of black holes, time dilation serves as a powerful reminder of how these cosmic giants challenge and reshape our understanding of the universe. Next, we'll take a closer look at the challenges of retrieving information from black holes and the theories that attempt to solve this puzzle. Shifting our attention to the next puzzle, let's dive into the black hole information retrieval problem. This is one of the most perplexing challenges in modern physics. What happens to the information about objects that fall into a black hole? According to our current understanding, black holes are supposed to destroy information. But this contradicts a fundamental principle of quantum mechanics, that information cannot be lost. So, how do we reconcile these two ideas? One theory that attempts to solve this puzzle is the concept of soft hair. Proposed by physicists like Stephen Hawking and Andrew Strominger, soft hair refers to the idea that black holes have a kind of fuzz on their event horizons, subtle imprints left by particles that fall in. These imprints could potentially store information about what enters the black hole, acting like a cosmic fingerprint. While this theory is still in its early stages, it offers a promising way to preserve information without breaking the laws of physics. Another intriguing possibility is quantum tunneling. In quantum mechanics, particles can sometimes pass through barriers that would be impossible to cross in classical physics. Some researchers suggest that information might escape a black hole through this process, tunneling out from the event horizon in ways we don't yet fully understand. This could mean that information isn't lost forever but instead leaks out over time, though detecting this would require breakthroughs in our observational technology. These theories are still being explored, and the black hole information retrieval problem remains an open question. However, they highlight the creative ways physicists are working to solve one of the universe's greatest mysteries. Understanding how information behaves in black holes could not only resolve this paradox, but also deepen our knowledge of the fundamental laws governing reality. As we continue to probe the secrets of black holes, the information retrieval problem serves as a reminder of how these cosmic enigmas push the boundaries of science. Next, we'll examine the mind-bending idea that black holes might be connected to a multiverse, opening up even more possibilities for our understanding of the cosmos. Turning our gaze to another fascinating possibility, let's explore the idea that black holes might serve as gateways to a multiverse. The concept of a multiverse suggests the existence of countless other universes beyond our own, each with its own unique laws of physics. But how could black holes fit into this picture? One intriguing theory proposes that black holes could act as bridges between these parallel realities, creating a cosmic network of interconnected universes. At the heart of this idea is the concept of wormholes, hypothetical tunnels in space-time that could connect distant points in the universe, or even different universes altogether. While wormholes remain purely theoretical, some physicists argue that black holes might naturally form these structures under extreme conditions. If this is true, black holes could be more than just destructive forces. They might be portals to entirely new realms. The implications of this theory are profound. If black holes do connect to a multiverse, it could revolutionize our understanding of cosmology. It would suggest that our universe is just one piece of a much larger puzzle, with black holes acting as the threads that weave it all together. This idea also raises questions about the nature of reality itself. Could information or even matter travel between universes through these black hole portals? And what would that mean for the fate of our own universe? While the multiverse hypothesis is still speculative, it's supported by certain interpretations of quantum mechanics and string theory. These frameworks suggest that the universe we inhabit is just one of many, each with its own set of physical constants and properties. Black holes, with their extreme gravitational forces and mysterious interiors, might be the key to unlocking this vast cosmic tapestry. As we continue to unravel the mysteries of black holes, the possibility of a multiverse connection opens up exciting new avenues for exploration. It challenges us to think beyond the boundaries of our own universe and consider the limitless possibilities that might lie hidden within these cosmic enigmas. Next, we'll dive into the entropy paradox, another mind-bending puzzle that black holes present to physicists. Now, let's shift our focus to a perplexing question that challenges our understanding of black holes, the entropy paradox. Entropy, a concept from thermodynamics, measures the amount of disorder or randomness in a system. It's a fundamental idea that helps explain how energy spreads and systems evolve. But when it comes to black holes, things get puzzling. How can an object that's supposed to be the ultimate vacuum of space have entropy? At first glance, black holes seem like the opposite of entropy. They're often described as simple, with their properties reduced to just mass, charge, and spin. Yet, physicists like Jacob Bekenstein and Stephen Hawking discovered that black holes do, in fact, have entropy. In fact, they have a lot of it. The entropy of a black hole is directly proportional to the area of its event horizon, an idea that seems to defy our intuitive understanding of disorder. This discovery led to the famous Bekenstein-Hawking formula, which calculates the entropy of a black hole. But here's the twist: entropy usually requires information about the microscopic states of a system. For example, the entropy of gas in a room depends on the positions and velocities of its molecules. But with black holes, where all matter and energy are crushed into a singularity, it's unclear what these microscopic states could be. This is the heart of the entropy paradox. The paradox deepens when we consider quantum mechanics. According to quantum theory, information can never be truly destroyed. Yet, when matter falls into a black hole, it appears to vanish forever, taking its information with it. This contradiction hints at a fundamental conflict between thermodynamics and quantum mechanics, two cornerstones of modern physics. One proposed solution to this paradox is the idea of holography, which suggests that all the information about a black hole's interior could be encoded on its surface, the event horizon. This aligns with the holographic principle, a theory that posits the universe itself might function like a hologram, with lower dimensional surfaces encoding higher dimensional realities. If true, it could resolve the entropy paradox by showing that black holes don't destroy information but rather store it in a way we're only beginning to understand. The implications of this paradox are far-reaching. It forces us to rethink the nature of black holes and the fundamental laws of physics. It also bridges the gap between thermodynamics and quantum mechanics, two fields that have long struggled to reconcile their differences. As we delve deeper into this mystery, we might uncover not just the secrets of black holes, but also new insights into the fabric of the universe itself. Up next, we'll explore the role of supermassive black holes in shaping galaxies, shedding light on their immense influence over cosmic structures. Moving forward, let's turn our attention to the colossal giants lurking at the hearts of galaxies, supermassive black holes. These immense objects, often millions or even billions of times more massive than our Sun, are not just cosmic curiosities. They play a pivotal role in the evolution of galaxies, shaping them in ways we're only beginning to comprehend. Supermassive black holes are believed to form through a combination of processes. One theory suggests they grow from smaller black holes that merge together, accumulating mass over billions of years. Another idea is that they form directly from the collapse of massive gas clouds in the early universe. Whatever their origin, these black holes are now found at the centers of nearly every large galaxy, including our own Milky Way. But what makes supermassive black holes so influential? One key factor is their gravitational pull. Their immense mass can affect the motion of stars and gas within their host galaxies, creating a dynamic environment. For instance, as gas and dust fall toward the black hole, they form an accretion disk, a swirling ring of material that heats up and emits enormous amounts of energy. This energy can push away surrounding gas, effectively regulating star formation in the galaxy. In some cases, supermassive black holes can even trigger the birth of new stars. While their energy can suppress star formation in certain regions, it can also compress gas in other areas, creating the conditions needed for stars to form. This dual role, both nurturing and limiting star formation, highlights the complex relationship between black holes and their galaxies. Another fascinating aspect of supermassive black holes is their jets. These are streams of particles and radiation that shoot out from the poles of the black hole's accretion disk, often extending far beyond the galaxy itself. These jets can travel at nearly the speed of light and impact their surroundings in dramatic ways. They can heat up interstellar gas, influence the shape of the galaxy, and even affect the growth of other black holes in the vicinity. The presence of supermassive black holes also appears to be linked to the overall structure of galaxies. Observations show that galaxies with more massive black holes tend to have larger bulges of stars at their centers. This correlation suggests that black holes and galaxies co-evolve, with each influencing the other's growth and development. Understanding supermassive black holes is crucial for piecing together the story of galactic evolution. They are not just passive observers but active participants, shaping the cosmos on an unimaginable scale. As we continue to study these cosmic giants, we uncover more about the intricate dance between black holes and the galaxies they call home. Next, we'll explore the groundbreaking image of a black hole shadow captured by the Event Horizon Telescope and what it reveals about these mysterious objects. Now, let's take a closer look at one of the most groundbreaking achievements in modern astronomy, the first ever image of a black hole shadow. Captured by the Event Horizon Telescope in 2019, this remarkable image provided humanity with a visual glimpse of the invisible. But what exactly are we seeing, and why is it so significant? The black hole shadow isn't the black hole itself, but rather the dark silhouette created by the event horizon. The point of no return where even light cannot escape the black hole's immense gravitational pull. Surrounding this shadow is a bright ring of light, which is actually the accretion disk of superheated gas and dust swirling around the black hole. This ring of light is bent and distorted by the black hole's gravity, creating a visual effect known as gravitational lensing. The Event Horizon Telescope, a global network of radio telescopes, made this historic capture possible. By combining data from telescopes around the world, scientists essentially created a virtual telescope the size of Earth, capable of resolving incredibly fine details. The black hole they imaged, located in the galaxy Messier 87, is 55 million light-years away and has a mass 6.5 billion times that of our Sun. This image isn't just a stunning visual, it's a treasure trove of scientific insights. For one, it confirmed predictions made by Einstein's theory of general relativity more than a century ago. The shape and size of the shadow matched Einstein's equations with remarkable precision, providing strong evidence for his description of how gravity warps space and time. Additionally, the image revealed details about the black hole's spin and the orientation of its accretion disk. These observations help scientists better understand how black holes consume matter and emit powerful jets of energy. The data also supports the idea that all black holes, regardless of their size, share similar fundamental properties. The success of the Event Horizon Telescope has opened up new possibilities for studying black holes. Future observations aim to capture images of other black holes, including the one at the center of our Milky Way, known as Sagittarius A star. These images could provide even more insights into the behavior of black holes and their role in shaping the universe. This milestone reminds us of the power of collaboration and innovation in science. By pushing the boundaries of technology and human ingenuity, we've taken a giant leap toward unraveling the mysteries of these enigmatic cosmic objects. Next, we'll explore how black holes might hold the key to understanding one of the greatest challenges in physics, the quest for a theory of quantum gravity. Now, let's turn our attention to one of the most profound challenges in modern physics, the quest to unify general relativity with quantum mechanics. At the heart of this effort lies the study of black holes, which could hold the key to understanding quantum gravity. While general relativity beautifully describes the large-scale behavior of gravity, quantum mechanics governs the microscopic world of particles and forces. Black holes, with their extreme gravitational fields and tiny scales, are the perfect testing grounds for reconciling these two seemingly incompatible theories. One of the central puzzles in this area is the nature of the singularity at the core of a black hole. According to general relativity, the singularity is a point of infinite density where the laws of physics break down. However, quantum mechanics suggests that such infinities shouldn't exist. This contradiction hints that a deeper theory, quantum gravity, is needed to explain what truly happens at the heart of a black hole. One promising approach is string theory, which proposes that particles are tiny, vibrating strings. In this framework, black holes could be made up of these strings, providing a quantum description of their structure. Another idea is loop quantum gravity, which suggests that space itself is quantized into discrete units, potentially preventing the formation of singularities. Both theories aim to describe black holes in a way that respects the principles of quantum mechanics while accounting for their immense gravitational effects. Black holes also offer insights through phenomena like Hawking radiation. This process, predicted by Stephen Hawking, suggests that black holes emit particles due to quantum effects near the event horizon. This radiation carries information about the black hole's properties, potentially offering clues about quantum gravity. However, it also raises questions about what happens to information that falls into a black hole, a problem known as the information paradox. Solving this paradox could be a major step toward a unified theory. By studying black holes, scientists hope to uncover the fundamental principles that govern the universe at both the largest and smallest scales. These cosmic enigmas might not only bridge the gap between general relativity and quantum mechanics, but also reshape our understanding of space, time, and reality itself. As we continue to explore these ideas, black holes remain a powerful lens through which we can glimpse the deepest secrets of the cosmos. Next, we'll examine how the concept of black hole complementarity adds another layer to this fascinating puzzle. Turning our gaze to another intriguing concept, we encounter the black hole complementarity principle, a theory that attempts to resolve one of the most puzzling aspects of black holes: what happens to information that falls into them. At first glance, this idea seems paradoxical. On one hand, quantum mechanics tells us that information can never be truly lost. On the other hand, general relativity suggests that anything crossing the event horizon of a black hole is gone forever. So, which is it? The complementarity principle offers a fascinating solution: both. According to this theory, information falling into a black hole is both preserved and destroyed, but not in the way you might think. From the perspective of an outside observer, the information never actually enters the black hole. Instead, it appears to be smeared across the event horizon, encoded in a way that preserves it. However, for someone falling into the black hole, the information is indeed lost as they cross the event horizon. This dual perspective complementarity means that both descriptions can be true simultaneously, depending on the observer's frame of reference. This principle challenges our traditional notions of reality, suggesting that the nature of information and space-time might be far more flexible than we once believed. It also provides a potential resolution to the infamous information paradox, which has puzzled physicists for decades. If the complementarity principle holds true, it would mean that black holes don't destroy information, they simply store it in a way that's inaccessible to us. However, this theory isn't without its controversies. Some physicists argue that complementarity relies on untested assumptions and may not fully account for the complexities of quantum mechanics and gravity. Others see it as a stepping stone toward a more complete theory of quantum gravity, one that could finally reconcile the fundamental laws of the universe. The implications of the black hole complementarity principle extend far beyond black holes themselves. If information can exist in multiple states simultaneously, it could revolutionize our understanding of space, time, and even the nature of reality. As we continue to probe these mysteries, black holes remain a powerful tool for unlocking the deepest secrets of the cosmos. Next, we'll explore another captivating theory: the role of black holes in the Big Bang. Shifting our focus to an even grander scale, let's delve into a theory that ties black holes to the very birth of the universe, the Big Bang itself. This idea suggests that black holes, or something resembling them, might have played a pivotal role in the explosive event that set our cosmos into motion. It's a concept that bridges the infancy of the universe with the enigmatic objects we're still trying to understand today. The theory proposes that black holes or black hole-like structures could have existed in the earliest moments of the universe, possibly even before the Big Bang. Some physicists speculate that these objects might have acted as seeds, triggering the massive expansion we now call the Big Bang. Imagine a universe so dense and hot that black holes could form almost instantly, their immense gravity pulling in matter and energy, and then somehow releasing it in a colossal explosion. One line of thinking involves a concept known as quantum tunneling. where black holes could have transitioned from a highly compressed state into the expanding universe we see today. This process would have released vast amounts of energy, driving the rapid inflation of space. Another idea suggests that black holes might have contained remnants of a previous universe, acting as bridges between cosmic cycles in a multiverse scenario. While these ideas might sound like science fiction, there's some theoretical groundwork to support them. For instance, the equations of general relativity and quantum mechanics hint at conditions in the early universe where such phenomena could occur. Additionally, the presence of supermassive black holes in the centers of galaxies, some of which formed astonishingly early in cosmic history, raises questions about their origins and potential connection to the Big Bang. This theory also opens up fascinating possibilities for understanding the universe's initial moments. If black holes were indeed involved in the Big Bang, they might have left behind telltale signatures in the cosmic microwave background, the faint afterglow of the early universe. Detecting such signals could provide crucial evidence for this idea, although it remains a formidable challenge for astronomers and physicists. As with many theories about black holes, this one pushes the boundaries of our imagination and scientific understanding. It invites us to reconsider not just what black holes are, but how they might have shaped the very fabric of reality. Next, we'll explore another intriguing theory, the black hole mirror universe connection, and how it could redefine our perception of the cosmos. Moving into another fascinating layer of black hole mysteries, let's consider the idea that these cosmic giants might have a connection to a mirror universe. This theory takes the concept of parallel universes to a whole new level, suggesting that black holes could serve as gateways to an entirely flipped version of reality. The mirror universe theory proposes that beyond the event horizon of a black hole, there might exist a universe where the laws of physics are inverted. In this alternate reality, time could flow backward, particles might behave as their antimatter counterparts, and even the very fabric of space could be fundamentally different. It's a mind-bending idea that challenges our understanding of how the universe operates. One possible explanation for this connection lies in the mathematics of general relativity. When scientists model the interior of a black hole, the equations sometimes suggest the existence of a mirrored counterpart. This doesn't necessarily mean a literal mirror, but rather a space where the properties of matter and energy are reversed. Some researchers even speculate that black holes could be points where two universes are stitched together, allowing for a cosmic passage between them. The implications of this theory are staggering. If black holes truly connect to a mirror universe, it could explain some of the mysteries surrounding their behavior, such as where the information that falls into a black hole ultimately goes. Instead of being destroyed, it might simply re-emerge in this alternate reality, preserved in a form that defies our current understanding. While this idea remains speculative, it's not without theoretical support. Certain interpretations of quantum mechanics and string theory hint at the possibility of mirrored spaces, and the concept aligns with the idea of a multiverse, a collection of countless parallel realities. However, proving such a connection would require groundbreaking discoveries, potentially including observations of black hole behavior that defy conventional physics. This theory also raises profound questions about the nature of existence. If a mirror universe exists, could it have its own stars, galaxies, and life forms? And if so, how might that reshape our place in the cosmos? It's a concept that blurs the line between science and philosophy, inviting us to rethink everything we know about reality. As we continue our exploration of black hole theories, this one stands out for its sheer imaginative scope. It reminds us that the universe is far stranger and more complex than we often imagine. Up next, we'll delve into how black holes might influence the arrow of time itself, adding yet another layer to their enigmatic nature. Now, let's shift our focus to how black holes might play a role in shaping the arrow of time, a concept that defines the direction in which time moves. Typically, we experience time as a one-way journey from the past to the future, but black holes with their extreme gravitational forces could challenge this understanding. One of the key ideas here is entropy, which is a measure of disorder in a system. According to the second law of thermodynamics, entropy always increases over time, and this is often linked to the arrow of time. Black holes with their immense gravitational pull could influence entropy in profound ways. For instance, as matter falls into a black hole, it adds to the black hole's entropy, potentially altering the flow of time in its vicinity. Another aspect to consider is causality, the relationship between cause and effect. Near a black hole, the intense gravity could distort cause and effect, making it difficult to determine which event happened first. This raises the question of whether black holes could create regions where time behaves in unexpected ways, perhaps even looping or reversing under extreme conditions. The thermodynamics of time also comes into play when examining black holes. Hawking radiation, the process by which black holes lose mass over time, suggests that black holes have their own thermodynamic properties. This loss of mass could influence the arrow of time, as the black hole's energy is slowly released back into the universe, potentially creating a feedback loop that affects the flow of time itself. These ideas are still largely theoretical, but they open up fascinating possibilities. If black holes can influence the arrow of time, it could mean that time isn't as straightforward as we think. It might flow differently in different parts of the universe, shaped by the presence of these cosmic giants. As we explore these concepts, it's clear that black holes continue to challenge our understanding of time, space, and reality itself. Up next, we'll take a closer look at the mysteries hidden within the interior of black holes, including the nature of the singularity and the puzzles it poses to modern physics. Now, as we venture deeper into the enigmatic world of black holes, let's turn our attention to the very heart of these cosmic phenomena, the black hole interior and the singularity. This is where the rules of physics as we know them begin to break down, and where some of the greatest mysteries of the universe lie hidden. At the center of every black hole lies the singularity, a point where density becomes infinite and the laws of physics cease to function. According to Einstein's theory of general relativity, the singularity is where all the mass of the black hole is concentrated into an infinitely small space. This creates a region where gravity becomes so extreme that not even light can escape, and space-time itself is warped beyond recognition. But the singularity isn't just a point of infinite density, it's also a point of infinite confusion for physicists. The equations that describe it simply stop working, and our current understanding of the universe falls apart. This raises the question of whether our theories are incomplete, or if there's something fundamentally different about the nature of the singularity that we're missing. One of the biggest challenges in studying the black hole interior is that it's completely hidden from us. The event horizon, the boundary around a black hole, acts as a one-way door. Once something crosses it, there's no way to send information back out. This means we can't directly observe what happens inside a black hole, and we're left to rely on theoretical models and mathematical predictions. Some theories suggest that the singularity might not be a point at all, but a ring or even a more complex structure. Others propose that quantum effects could prevent the formation of a true singularity, replacing it with something entirely different, like a quantum foam or a gateway to another dimension. These ideas are still speculative, but they highlight just how much we have yet to learn about the interior of black holes. As we ponder these mysteries, it's clear that the black hole interior and singularity remain one of the most profound puzzles in modern physics. They challenge our understanding of the universe and push us to rethink the very foundations of science. Next, we'll explore another fascinating aspect of black holes, Hawking radiation, and how it might hold the key to unraveling some of these mysteries. Now, shifting our focus to the outer edges of black holes, we encounter one of the most revolutionary ideas in modern physics, Hawking radiation. named after the renowned physicist Stephen Hawking, this theory suggests that black holes are not entirely black after all. Instead, they emit a faint form of radiation that causes them to lose mass over time. But how does this happen, and what does it mean for the fate of black holes? Hawking radiation arises from the strange interplay between quantum mechanics and gravity near the event horizon of a black hole. In the quantum world, space is not empty. It's filled with pairs of particles and antiparticles that constantly pop into existence and annihilate each other. Near the event horizon, one of these particles can fall into the black hole while the other escapes into space. The escaping particle carries away energy, which gradually reduces the black hole's mass. This process has profound implications for the life cycle of black holes. Over incredibly long timescales, Hawking radiation could cause a black hole to completely evaporate, leaving behind nothing but a faint burst of energy. This challenges the old idea that black holes are eternal and unchanging, suggesting instead that they have a finite lifespan. But this raises another question: what happens to all the information that fell into the black hole? The information paradox, which we discussed earlier, becomes even more puzzling in the context of Hawking radiation. If a black hole evaporates, does the information it swallowed vanish forever, violating the laws of quantum mechanics? Or is there a way for the information to escape, perhaps encoded in the radiation itself? This remains one of the most hotly debated questions in physics, with no definitive answer yet. Stephen Hawking's discovery not only transformed our understanding of black holes, but also opened up new avenues for exploring the connections between quantum mechanics and gravity. It's a reminder that even the most mysterious objects in the universe are governed by fundamental laws waiting to be uncovered. Next, we'll delve into an even more mind-bending idea: the possibility that black holes could be holographic projections of the universe itself. Now, let's venture into a concept that blurs the line between science and philosophy: the black hole hologram connection. This theory proposes that black holes might not be the three-dimensional objects we imagine, but instead holographic projections of the universe itself. At its core, this idea stems from the holographic principle, which suggests that all the information contained within a black hole could be encoded on its two-dimensional surface, much like a hologram. Imagine a holographic image. It appears three-dimensional, but it's actually a flat surface storing all the data needed to create that illusion. Similarly, the holographic principle suggests that the three-dimensional reality we perceive could be encoded on a two-dimensional boundary, like the event horizon of a black hole. This radical idea challenges our understanding of space, time, and the very nature of reality. So, how does this work? According to this theory, the information about everything that falls into a black hole isn't lost forever, but is instead smeared across its surface. This could solve the information paradox we discussed earlier, as the data would still exist, just in a different form. It's a bit like taking a three-dimensional object and flattening it into a two-dimensional picture. All the details are still there, just rearranged. The implications of this theory are profound, not just for black holes, but for our understanding of the universe as a whole. If black holes are holographic, could the entire universe be a hologram too? Some physicists argue that the holographic principle might apply on a cosmic scale, suggesting that the universe itself could be a projection of information stored on its boundaries. This idea bridges physics and philosophy, raising questions about the nature of existence and the limits of human perception. While the holographic principle remains a speculative idea, it has sparked fascinating debates and experiments. Scientists are exploring ways to test this theory, from studying the properties of black holes to probing the fundamental nature of space-time. It's a reminder that the most profound questions in physics often lead us to rethink not just the universe but our place within it. Next, we'll explore the ultimate fate of black holes, whether they vanish, collide, or play a role in the universe's final moments. Shifting our focus to the grand cosmic finale, let's explore one of the most intriguing questions in astrophysics. What happens to black holes in the end? The ultimate fate of black holes isn't just a question about these mysterious objects, it's a window into the destiny of the universe itself. One of the most widely discussed theories is black hole evaporation, a process first proposed by Stephen Hawking. According to this idea, black holes aren't completely eternal. Over unimaginable stretches of time, they slowly lose mass through a phenomenon called Hawking radiation. This radiation occurs because of quantum effects near the event horizon, where pairs of particles and antiparticles pop into existence. Occasionally, one particle falls into the black hole while the other escapes, carrying away a tiny bit of the black hole's energy. Over trillions upon trillions of years, this process could cause a black hole to shrink and eventually vanish, leaving behind only a faint burst of radiation. But evaporation isn't the only possibility. Another fascinating scenario involves black hole collisions. In the vast expanse of the universe, black holes can and do collide, merging into even more massive objects. These collisions send ripples through space-time, known as gravitational waves, which we've only recently begun to detect. When two black holes collide, they don't just combine their masses, they also create a spectacular display of energy that can be felt across the cosmos. Over time, as galaxies merge and stars die, black holes might continue to collide, growing larger and more dominant. Some scientists speculate that in the far, far future, the universe could be filled with supermassive black holes, each one a remnant of an entire galaxy. Then there's the question of black holes and the universe's ultimate fate. If the universe continues expanding forever, as some theories suggest, black holes might be among the last objects left in an increasingly cold and empty cosmos. In this distant future, black holes could play a role in the universe's final moments. Some theories even suggest that black holes might be the seeds of a new universe, with their immense gravitational fields creating the conditions for a new Big Bang. This idea ties black holes directly to the cosmic cycle of birth, death, and rebirth. While these theories are still speculative, they offer a glimpse into the profound mysteries of black holes and their place in the universe. Whether they evaporate, collide, or spark the birth of a new cosmos, black holes remain one of the most fascinating subjects in science, challenging us to rethink our understanding of time, space, and existence itself. Now, let's take a closer look at the mechanics behind one of the most captivating theories, black holes as portals to other universes. At the heart of this idea is the concept of the Einstein-Rosen bridge, often referred to as a wormhole. This theoretical passageway connects two distant points in space-time, potentially allowing travel between them. The idea is that a black hole could act as one end of this bridge, with its immense gravity warping space-time to create a tunnel-like structure. But here's the catch: for a wormhole to be traversable, it would need to remain stable, and that's where exotic matter comes into play. Exotic matter is a hypothetical substance with negative energy density, which could theoretically counteract the immense gravitational forces that would otherwise collapse the wormhole. Without this exotic matter, the wormhole would likely snap shut instantly, making it impossible to traverse. While we've yet to discover or create such matter, its existence is a key part of making the black hole portal theory plausible. Another challenge is the extreme conditions near the event horizon, where tidal forces would stretch and compress anything entering the wormhole, posing significant risks to any potential traveler. Interestingly, some scientists suggest that quantum mechanics might offer a way to stabilize wormholes. Quantum entanglement, for instance, has been proposed as a mechanism that could help maintain the structure of a wormhole, at least in theory. While these ideas remain speculative, they open up fascinating possibilities for how black holes could serve as gateways to other universes or distant regions of our own. The role of black holes as portals challenges our understanding of space-time, gravity, and the very fabric of the cosmos, offering a tantalizing glimpse into what might lie beyond the event horizon. Now, shifting our focus to another fascinating area, let's delve into how scientists are testing the holographic principle. This groundbreaking idea suggests that all the information contained within a black hole is encoded on its surface, much like a hologram. But how do we move from theory to evidence? One approach involves studying the event horizon itself, the boundary that marks the point of no return for anything entering a black hole. Researchers are looking for patterns or fluctuations in the event horizon that could reveal how information is stored or projected, providing clues to support the holographic principle. Another key area of investigation is through gravitational waves, the ripples in space-time caused by massive cosmic events like black hole collisions. By analyzing these waves, scientists hope to detect signatures that align with the holographic principle's predictions. For instance, if the echoes or patterns in gravitational waves match what the theory anticipates, it could serve as strong evidence in its favor. Additionally, experiments in quantum physics are shedding light on this concept. Laboratory setups that mimic the behavior of black holes on a smaller scale are being used to test whether information can indeed be encoded and retrieved from a two-dimensional surface. These experiments, though still in their early stages, offer a promising way to explore the holographic principle in a controlled environment. While these methods are still evolving, they represent crucial steps toward understanding whether our universe truly operates like a hologram. The implications of this principle are profound, challenging our perception of reality and opening up new avenues for exploring the nature of space, time, and information. As research continues, we may find ourselves closer to answering one of the most profound questions in physics. Is our universe a holographic projection? Now, moving into another intriguing area, let's explore what lies beyond the no-hair theorem. This principle suggests that black holes can be fully described by just three properties: mass, charge, and spin. But what if there's more to it? Some alternative theories propose that black holes might possess additional characteristics, challenging this long-standing idea. One such theory suggests that black holes could have soft hair, a term coined by physicists to describe subtle quantum effects on the event horizon. These soft hair properties might carry information about particles that have fallen into the black hole, offering a potential solution to the information paradox. This idea opens up new possibilities for understanding how black holes store and process information. Another fascinating concept is the idea of hidden symmetries within black holes. These symmetries, if they exist, could imply that black holes have more complex structures than previously thought. Researchers are investigating whether these symmetries could reveal additional properties, such as internal oscillations or unique energy signatures, that go beyond the simple description of mass, charge, and spin. Additionally, some theories explore the possibility of black holes having quantum hair, a term referring to quantum mechanical features that could leave imprints on the gravitational field. If proven, this would mean that black holes are far richer in complexity than the no-hair theorem suggests, potentially reshaping our understanding of their nature. These alternative theories are still in the realm of speculation, but they highlight the excitement and uncertainty surrounding black hole physics. As scientists continue to push the boundaries of our knowledge, we may discover that black holes hold secrets far beyond the simplicity of the no-hair theorem. This ongoing exploration keeps us on the edge of uncovering the true nature of these cosmic phenomena. As we reach the end of our journey through 25 mind-bending theories about black holes, it's clear that these cosmic giants are far more than just gravitational traps. From the possibility of black holes serving as portals to other universes to their potential role as dark matter factories, each theory challenges our understanding of reality and pushes the boundaries of physics. The mysteries of Hawking radiation, the holographic principle, and the nature of singularities remind us just how much we have yet to uncover. Black holes are not just astronomical phenomena, they are gateways to some of the most profound questions about the universe. Thank you for joining me on this exploration of the unknown. If these theories sparked your curiosity, let me know in the comments which one fascinated you the most. Don't forget to subscribe and hit the notification bell so you never miss a journey into the cosmos. Together, we'll continue unraveling the secrets of the universe, one theory at a time. Until next time, keep looking up and wondering what lies beyond the stars.